between what is happening, between your boundary conditions and the equations you write in the bulk. Right? So this here, when you're writing the velocity is equals to gradient of phi, you're inside of the fluid and you say there, the flow is irrotational, my velocity derives from a potential. Here, this is mass conservation. Again, you write this in the bulk, right? Now, the boundary condition, you always only write at the boundary. So, the velocity in the z direction is only 0 at the boundary. It's a no penetration boundary condition. It might be non-zero in the bulk. And this equation here is also only valid at the boundary. This is your kinematic boundary condition. And then that normal stress boundary, the normal stress balance is also only at the boundary because it's your boundary condition. Now the statement of momentum conservation, this is in the bulk. This is in any location inside of the fluid. Now you see, you actually, at this point, you see sort of where this will come in. Once we know what phi is, we know what the velocity is. Remember that u, so this u here is really the norm of u. Usually this is how it's represented. So it's the norm of the gradient of phi. So you could also write this u squared as the norm of the gradient of phi squared. Yeah. This one here we'll write also. We can write in the bulk, but you see that the only place where we'll be really interested in knowing the pressure is at the boundary, because this is where we impose the pressure. But this is where we impose the boundary condition. So this is true in the bulk, in the fluid, and by extension, right at the boundary. This is also true. This will hold at the boundary, and in particular, we'll be interested in the pressure at the boundary, because this is where we'll relate everything which is happening in the fluid, the gravity, the effect of gravity, inertia, to the effect of surface tension. Okay, so we'll solve this by making an assumption for how the solution will look, and I will make an ansatz for small perturbation wave theory. Right, and so you can always think that your interface gets disturbed, right? And the best I can do is just to say, that any kind of shape, you could Fourier transform that and split it into a superposition of sinusoidal-looking waves. Right? So we'll make an assumption for a particular wave of a particular wavelength. Right? You could think that the interface, so h, for instance, at t equals 0 and x will look like a cosine. So like a cosine kx. Now this k here is unknown. It's just completely random. And actually really what you want to think about is that your interface is going to be a summation of these over all wavelengths. Right? You could have any wavelengths, big and small. Actually, when you look at the ocean, you see several wavelengths. You see the small waves, but then you also see in between like larger waves. Right? So you have more than one wavelength. Okay, so we have this. And so the ansatz that we will make for phi, we'll assume and we'll try to find phi, our potential, under the form of a function of z times, really what we would want is a cosine, but we'll play with exponential. So you could want to find it as the cosine minus omega t, or minus ct. It's the same. But what we'll do is we'll play with exponential because it's going to be easier. So k x minus ct. So we are assuming that we are looking for a solution under this form. Now, why are we assuming this form? This is again because applied mathematicians have worked very long hours to come up with that ansatz, which actually works. So once we plug that in, we'll see that we can find a solution under that form. Right, so this is again not something which is expected from you in this class. You're trained as engineers. You design cars, you design power plants, and the applied mathematicians are very thankful that they can drive and that they can have electricity. Right? Applied mathematician, on the other hand, they derive ansatz solutions and methods, to change your PDEs into ODEs that then you can use in your engineering class. So everybody has its role. You're not expected to know all of these things. This is really what applied mathematicians do. Okay. So what we just do is we'll just use that form and we'll plug it in and we'll see what condition that gives us on our waves. Now, it's important that from the beginning, you'll see that there are a few things here which are unknown. What is unknown is A. What is this function here? And most importantly, what the two things which are unknown are K and C. We are putting in a random wave number, so something which looks like, which look at the interface as a sine of a certain wavelength, and we're just saying this is going to propagate at the velocity c. Right? What we are trying to find out is that for a given wave number or for a given wavelength, at which velocity is this going to propagate? Okay, so right now we're putting in random numbers, but what we want in the end is to be able to relate this wave number to that wave velocity, and you'll see that that depends on the configuration of your flow, whether h is very large, the depth of your bath is very large, whether surface tension is important or not. So you'll see that in the end, this is what we are aiming at. We are aiming for k or c as a function of k. This is what we want to find out. We want to find out c as a function of k. Okay. Good. So now we'll take things one by one, and so we'll derive the solution. Okay, and the first thing we'll do is we'll make sure that this is indeed satisfies the mass conservation. Okay, so we want to make sure that we have the Laplacian of phi equal to 0. So we take our ansatz, well, assumption. An ansatz is essentially an educated guess. You take our educated guess, you put it into your Laplace equation. So you have the second partial with respect to x plus the second partial with respect to z of phi. So when I take the second partial with respect to x, I get a double prime of z times exponential I kx minus ct. This is the second partial with respect to x, and this is the second partial with respect to z. When I take the second partial with respect to x, I have to multiply twice the exponential by ik, so I get a minus k squared az plus the second derivative with respect to z of exponential I k x minus ct. And that has to be equal to 0. So just note that this is my second partial with respect to x, and this here is my second partial with respect to z. Okay, so you can factorize the exponential and when you factorize the exponential, you're left with a second order ODE. So you're left with the second derivative of a with respect to z minus, or let me say equal to, k squared times az, right? And so this here, the solutions for that will be hyperbolic cosines and sines. So we know that az is going to be equal to a combination of a hyperbolic cosine plus b, let me put alpha, plus alpha hyperbolic sine of kz. Okay, this is going to be the form for az, and therefore our potential, right, is going to be equal to that. sine times h z. Sorry, so I have a hyperbolic sine, and here I have a k. I have a hyperbolic sine, and here I have a k, times exponential I kx minus ct. This is what the solution is going to look like. This is the first thing that we imposed, and the second thing we'll impose is directly I'm lost in my numbering. It's going to be the no penetration boundary condition at the bottom. So let me see, the number is 4. Yeah. So impose 4. No penetration at z equals minus h. So we know that partial phi over partial z, right, is equal to, oh, actually, I didn't want to write it this way. So let me just take a step back. Let me just rewrite that. So these here, they look like cosines and sines, right? So you know that for cosine and sine, you can say that I have a cosine phi plus b, a cosine t plus b cosine t. But you could also just put the sine into a phase. You could say, well, my general solution is going to be a cosine t plus a phase, right? It's the same thing. So we'll do the same thing here because it's going to be easier. So I'm going to assume that my solution here is going to be a times a hyperbolic cosine of kz, right, plus a z naught, right? This is a general. That would be a general way of writing it. Yeah? Or is that correct? I think it is, but I'm not sure. Okay, I think this is the form. I have no way of checking, so that's what we're going to play with, and we'll see. If it becomes too complicated, then I'll have to backpedal. Okay, z plus z naught. Okay, so this is a general solution. Now we want to impose our boundary condition at the bottom, so we have to say that partial phi over partial z at z equals minus h is going to be equal to 0. And this has to be true, of course, at all times and at all location x's. So let's compute partial phi over partial z. Partial phi over partial z will be equal to the exponential is not affected, so it's going to be equal to a times k times my hyperbolic sine of k z plus z naught times exponential I k x minus ct. That is equal to, and that has to be equal to 0 at z equals minus h, right? So our boundary condition then will become that a times k times the hyperbolic sine of k minus h plus z naught. Yeah, this is going to work. Exponential I k x minus ct is equal to 0. Right? So if this is equal to 0 for x to all the x and all the t's, which are not fixed, right? That means that this number here has to be equal to 0, right? And then if you remember the sign, the hyperbolic sign works like the sign when hyperbolic sign of 0 is equal to 0. That's what you have to remember. So one way of making this hyperbolic sign equal to 0 this is going to be equal to 0 if z naught is equal to h, right? So if whatever is here is equal to 0, yeah. So that identifies this z naught, and so after that we've made progress, and we know that our ansatz now for the solution looks like this. It looks like a hyperbolic cosine of z plus h. Remember, h here is the thickness of the water layer, I say water layer, but you could be talking about the whole ocean. So h could be very large. Hyperbolic cosine of z plus h exponential I k of x minus ct. Okay, so this is what we have. Now, let me just briefly show you how this works. Right, this is still an ansatz. We still haven't said anything about. We don't know what a is. We don't know what k is. We don't know what c is. Right, but this is essentially what our velocity field is going to look like. Here it's the potential. You take the gradient to get the velocity field. So let me show you briefly what this is. And the nice thing is that this, of course, satisfies. This potential satisfies the Laplace equation, and it satisfies our no penetration boundary condition at the bottom. And you'll see that this already looks like a wave. In principle, you'll see that. Okay. So just note here, I'm using the same routine that I gave you all the time. So I'm just creating this mesh, right? I'm just creating this mesh, and now I'm computing u and v, right? So you just take the solution that we have, just take the real part. I just take the cosine part. Right? I have an exponential I k x, but I'm just taking the cosine. You take partial phi over partial x. You'll get the u velocity. You take partial phi over partial z, you'll get the z velocity. So the partial phi over partial x gives you this guy here, right? You change your cosine x minus t becomes a sine, and your partial phi over partial z, your hyperbolic cosine becomes a hyperbolic sine, right? So this is exactly what we wrote on the board. Just take the gradient. And here you note that I just took random stuff. I took k equal to 1 and I took c equal to 1. Right? This k and this c are completely indeterminate. It could be anything at this point. But just so you see what this looks like, t now is going from 0 to 20, and the solution that we just derived looks like this. Okay? So it looks a bit like a wave. You have something which just propagates. And you see that you do have a no slip. You have a no penetration at the bottom, right? Note that we have imposed no boundary condition on the top surface. So this is the thing that we have left to do. We still need to impose a boundary condition on the top. Note also that the deformations are really small. You feel like there is a wave, but there is no wave. I'm just computing on a fixed grid, but sometimes you have a little velocity going upwards. This is why you feel like this is a wave, and that would correspond to a small displacement. But really, this displacement is really small. We're still in the limit where all of the deformation are just really small, so we completely neglect these. Now, the thing which you could already see from there, and this is tough to see, actually you can't see it probably, is that the only thing that really moves is the wave, is the interface. Right? If you now, that would be a good thing. Just take this velocity field and compute particle path lines, and you see that there is no mass movement. There is, but the mass just goes back in the circle. You see here, I mean, it's tough to see here, but let's start here. The flow starts going to the bottom, and then here it moves to the right, and then it's pushed up here, and then here, and now it moves to the left, and it comes back. So the flow, really the mass, the actual water just circulates underneath the surface, but the wave, the surface seems like it's propagating, but this is not a mass transport. Yeah? So these are the solutions that we are now going to plug into the boundary conditions, and what we are trying to get out is the relationship between the wave number, or the wavelength, and the wave speed. That's what we are going to do now. So every time, everything that we do, this is the solution that we essentially begin with. Okay, so the first boundary condition we have to satisfy is the no So now we have to look at the boundary condition on the top surface. So now boundary condition on top surface. And so this is where it could get confusing, because I'm going to say the top surface is at z equals 0. Right? Really, the top surface is not at z equals 0, it's at z equals h. Right? But because we assume everything to be small, you just have to think that if I have a function which is small, so phi is going to be small. Phi is our small disturbance of the velocity. Your phi is small and h is small. Right? H is small and phi is small. But if I take h at a small z, at z equals h, right? Then this is almost like phi at z equals 0, and phi, remember phi is small, times partial phi over partial z, which is also small, times h, which is small. Right? So you see here that really phi at z equals h is really just the same as phi equals 0, because taking phi as z as opposed to taking phi as h will make things much smaller. So whenever you're doing a small perturbation analysis, you look at the smallest, at the biggest small term. So you look at whatever, like phi, we're going to assume is small, h is small, so we'll look at this term. If you have anything which is the product of phi and h, or h squared, then this is small times small, this is really small, so those we neglect. So here, really because we're looking just at small perturbations, we'll just sit at z equals 0, because the difference we will have from being at z equals 0 and z equals h, because h is small, is going to be really small. Yeah? So this here is justified because we're looking a small perturbation. And you see that from Taylor extensions. Okay, now I really have to speed up, I think. So we have two equations to write. Partial phi equals u times partial phi over partial x. This equals to w. Now you already see that this is my kinematic boundary condition, and so this is no mass, no penetration at the boundary. Now you already see that here, this is small. This is going to be a partial phi over partial. This is h, sorry. Partial h, partial t, partial h, partial x. The u is going to be a partial phi, partial x. So this is small times small. Right, so that term here is really small. Here I just have one small, h, and I have w, just one small. So this equation in small perturbation just becomes partial h over partial t equals to w. Yeah. So at this point we can assume, you'll see that one way of satisfying that is to have h that looks like a wave propagating. So let me just compute w. So we have partial h over partial t. And w is going to be a, sorry, there should be a k here. Here there should be a k. So w is a times k hyperbolic sine of k z plus h, but here we are at z equals 0, times exponential I kx minus ct. Yeah? So note that this is now going to be a constant, so this is a k sine h times k times capital H exponential I kx minus ct. So this is where you realize that the mathematician did their job well, and that is because indeed, if I take a surface H, which is just a wave, so which just looks like exponential kx minus ct, then I can satisfy my kinematic boundary condition. Yeah? So you see that here. So let's assume then that H, so this can be satisfied with H equals to an H naught exponential I kx minus ct. Yeah? So that means that I would have a H naught times, now it's going to be an I, so my partial H over partial T becomes I kc exponential I kx minus ct, and this has to be equal to what we had before, which was A times K times, was it a hyperbolic sine, I think, of K capital H exponential I K of x minus ct. Yeah? So those here cancel, so our kinematic boundary condition gives us the first relation between H naught K. So see, here we have a first relation between K and C. Okay, so that's our relationship number one. This one I have marked down so I can check if it's correct.
Shouldn't there be a negative sign? Or isn't the minus case?
Yes, there is a, here you're right, there's a minus sign. So this is our first relationship. Okay, and now, okay, so this is the first relationship we get. So it's the first step towards getting a relation between K and C, but it's not done because we still have H naught floatings and A, and of course we know that we haven't put in the normal stress boundary condition, so we still don't have the effect of surface tension in all of that, right? So this is only part of the answer. Now we have to impose our second part. P atmosphere minus P is equal to gamma HXX. Now note, I'm going to have to go really quickly here because I just have the answer, so I'll just write the answer. This one I marked down. HXX is going to give you a, so remember that H is H naught exponential I kx minus ct. So it's going to be an IK squared, so it's going to be a minus H naught K squared, right? Exponential I K of x minus ct. So this term will give you a minus H naught times K squared, and this P, this is from Bernoulli. So now we're using Bernoulli, unsteady Bernoulli, at Z equals 0, right? So we're looking at the pressure to get to now. We look at the pressure underneath the surface. So P is going to be equal to a constant minus 1/2 of rho U squared plus rho G. Here I could say rho GH, right? You have to look at which one are the small terms. Hold on, am I missing a term here? And there's the partial T, minus, sorry, this is the one I was looking at. And there should be a minus sign here. Sorry, actually, I want to move those terms because I'm putting them in the wrong order. I forgot the unsteady term. So I have minus rho partial phi over partial T. Okay, so note we have to count how small things are. Phi is small, so that's fine. I have one small. U squared, what do you think is going to happen? This is going to be really small, right? Because U is small, then U squared is going to be very small, and here H is small. So I'm going to have small, small, and therefore this is going to be small. Everything is fine. So that term here is going to go to, this is here, very small, because this is small times small, it's double small. Note that this partial phi over partial t will give you a, again, minus I kc, will give you a minus I kc, right, times a sine blah blah, and this here will be h naught, exponential I kx minus ct, right, and you're plugging all of this into that equation, right, so this now, I'll let you do it yourself. This algebra is very doable, huh? And the equation you will get, this one I've written down, so let me just write that. Oh no, I haven't put it down. Oh yes, I have. Will give you minus I k c rho times a cosine k times h plus rho g h naught plus gamma h naught k squared equals 0. So this here, I'll just put arrows so that you can see. This term, so you have the pressure here, right? So this term comes from the pressure. So those two terms come from the pressure. This term here is your surface tension term, so it comes directly from here. This is this minus h naught k squared, so you have a gamma h naught k squared. This is that term here, and then through the pressure you have part of the unsteady term, which is this term here, and part of the gravity term, which is this term here. Yeah. So just do the algebra and you'll find this. And then if you, because I want to end up that quickly, otherwise we cannot even discuss the waves. So then so this is the second relationship. This is number 2. And so if you take 1 and 2 together, then you will end up, you can, if I take here, I can write a, here I can write a as a function of h naught. Let me just write that here. Here you could write a is equal to minus I h naught c divided by sine of k h, right? And so if you plug 1 into here, then you have everything with h naughts. The h naughts cancel, and you finally have a relationship between c and k, between your velocity, your wave speed, and your wavelength, which is what we wanted in the first place. Now this is where we started from, and that relationship becomes c squared. We get finally c squared is equal to g divided by k plus gamma times k divided by rho times hyperbolic tangent of k times h. So this is a very important relationship. And you can write it two ways, right? Either you can write it in terms of the wave number, but sometimes it's just easier because wave number is a bit less intuitive for me than wavelengths. So I'm just going to rewrite it in terms of the wavelength. So in terms of the wavelengths, it will be divided by lambda plus gamma lambda divided by 2 pi rho equals to the hyperbolic tangent of kh. Yeah, I did a mistake somewhere. Oh, yes. Oh, yeah, thank you very much. So now I'm confused again. So this is lambda divided by 2 pi, and this is lambda 2 pi gamma. Thank you. Okay, so this is our relationship. Okay, between our wave speed and our wave length. So the first thing that you would notice at this point is c squared here is always going to be positive. Lambda is a positive number, g is a positive number, gamma is a positive number, rho is a positive number, and the hyperbolic tangent of a positive number, this is not a pi, this is an h, kh, this is a positive number. So if c squared is a positive number, is it going to have an imaginary part? No, right? So what you have is any wave is not really going to be amplified. So you don't have this exponential minus imaginary part of c times t in front. So you don't have, from these equations at least, we don't have dissipation and we don't have growth. But what we have is just propagation. Okay, so the first thing to note here is that this here is always positive, which means that c is a real number. So in that configuration, what we have is that any disturbance is not going to grow or is not going to be dissipated. It's just going to propagate. So we really have waves. It's the first thing that explains to you why when you see a free interface and you throw a rock, the disturbance you create is something which propagates. At least the surface deformation propagates. The water underneath doesn't translate. That one doesn't propagate. You just have the surface, the surface disturbance propagates. So it's a real number, and therefore we have waves. This is the origins of gravity waves. This is the origin of what you see on the surface of the ocean, lake, your bath, anything. Okay, then you have two terms here. You have clearly here a gravity term, right? And you have here a surface tension term, right? Now, which one do you think is going to be important at the small scale? Which one do you think is going to be important at the large scale? Yes, so at the small scale, the surface tension will dominate. For smaller wavelengths, the surface tension term is going to dominate. For larger wavelengths, the gravity term is going to dominate. Right? Actually, if you take a ratio of the two, what do you get? If you take a ratio of those two terms, what do you get, do you think? Right, so if I take this term here, divided by that term here, I get lambda rho divided by gamma divided by divided by 1 divided by lambda g. So then I get this lambda squared times g. This here is a bond number, right? So remember that here is your bond number, so it's the relative importance of the gravity effect to surface tension effect. So when that bond number is small, the dominant effect is surface tension. When the bond number is large, the dominant effect is when the bond number is large, the dominant effect is gravity. When the bond number is small, the dominant effect is surface tension. So let's start with assuming that we can neglect, so number one, assume we can neglect the effect of surface tension. Okay. And that is going to be true for any wavelength which will be larger than, say, the capillary length. Remember, the capillary length is about 3 millimeters. So any waves that has a wavelength larger than that, say on the order of a centimeter or on the order of a meter, or the wave will be much larger than the capillary length, and therefore you assume that even if you think about this wave, the effect of surface tension are going to be negligible, because that as compared to the effect of gravity. So let's first neglect the effect of surface tension. I'm going to rewrite our relationship. This is our dispersion relationship, and so that is going to be just lambda g divided by 2 pi times tangent times, yeah, I have a k, but I don't want this k, so 2 pi h divided by lambda. Okay. The first thing which is important is you have two limits to that case, and that will depend on the relative wavelength. You have a wavelength. You have this ratio here. This is the important non-dimensional parameter. Is the ratio of your wavelength to the depth of your layer. So we'll first assume that you have deep water. And of course, it's always deep water compared to which length? It's compared to our wavelength. So when h divided by lambda is really large. So when h, and actually it doesn't take h to be too much larger than lambda. So let's say it's larger than 1 or larger than just a few units. Right? So do you remember, this is a hyperbolic tangent. Do you remember what hyperbolic tangent becomes when x becomes large? It becomes 1. Right? It becomes a ratio of the hyperbolic sine, so your hyperbolic cosine, it becomes 1, and actually it doesn't take a too large number here before the tangent reaches 1. Right? So when this is a bit larger than 1, then your hyperbolic tangent (2 pi over h divided by lambda) is going to be equal to 1. So this is very important, because then what is your wave speed going to depend? It's going to be equal to, sorry, am I doing this right now? Oh yes, this is becoming smaller wavelengths. That's fine. Yeah, so for smaller wavelengths, actually I wanted to start with the other, well, that's fine. Okay, let's start with that. This is okay. So then this is equal to lambda g divided by 2 pi. Right? The important thing here is to see that you see your wave speed, c, then is equal to the square root of lambda g divided by 2 pi. So your wavelength, your wave speed does depend on the wavelength. Right? So if you have a disturbance and you have, say, several wavelengths in there, then which waves propagate faster? Those with short wavelengths and those with large wavelengths? With large wavelengths, yeah? So those that have long wavelengths propagate faster than those that have small wavelengths. Here, c depends on lambda, right? So the larger lambda, the larger c. And in principle, this is what you should see when you throw a rock. So you throw a rock into the puddle, into a bath. You will see there's an initial disturbance. It had all kinds of wavelengths, and you'll see that the longer wavelengths are going to travel faster. And you'll see that closer to the object, you'll see the smaller wavelengths, they're going to travel a bit slower. So first of all, you'll see different wavelengths separate. Right? You'll see that at some point the wave is going to look like a superposition of waves, but the longer waves with the longer wavelength, they're going to go faster. You're going to see them coming out first, and then the shorter ones you're going to see come out later. They're going to move slower. Yeah. And then the last thing, so we'll finish that later on, but this is important. This is shallow water. That's the difference. So for shallow water, then here the hyperbolic tangent of x is roughly equal to x. So you know that c squared is equal to lambda g divided by 2 pi times 2 pi h divided by lambda. So you get something which does not depend. So then c is equal to the square root of g times h. The wave speed is independent on the wavelength. Right? And that is also a very important case. So, and this is the case when your wavelength is longer than your depth. Right? So when this number here, when h divided by lambda is small, right? Or that means that you have wavelengths, so you have long waves on the short bath. Now you've seen that probably when you were a kid, if you have just a thin layer of flow on an incline, then in principle what you see little riblets, if you've seen that before, and you really see clearly a riblet that's moving at a constant velocity, right? And that is because all of the different wavelengths that are in this wave, they move at the same velocity, so your features don't separate. So it looks like you have big waves. Or if you are in the ocean, the wave starts to really translate when you see a big feature moving like this. That's because all of the wavelengths which are in this big feature, they're all moving at the same velocity. Right? So close to the shore, then you will have shallow water, and this is when you see big features that move together. The different wavelengths which are in there, they don't separate because they don't move at different waves. That's the same when you have a tsunami. When you have a tsunami, what happens is that you have a dramatic event, right? So you think about the ocean about like a few kilometers, but you could create waves that have wavelength larger than a kilometer. And in that case, the waves don't separate, but you have this entire feature which just propagates and moves because all of the wavelengths inside move at the same velocity. Right? So this is when you have shallow water. And then we'll discuss capillary waves another time. Have a nice break.